This video is about YOLO object detection using a library called Image AI, and I'll also be using a little bit of OpenCV to do basic computer vision tasks. So to begin, here are some prerequisites. Make sure you have Image AI and OpenCV installed in your computer. You can download Image AI by following the link here and reading about the installation steps. In doing that, you'll also have to download OpenCV as well. Next, because I'll be using an Image AI library, I'll be using a pre-trained YOLO model. You should also go to this link here and download this YOLO model as well. And this model is what we'll be using to, it's a pre-trained model off the COCO data set. And that's what we'll be using for this whole the videos and the images that we'll be predicting on in this quick notebook demo here. As also another side note is that there are many different YOLO implementations out there. Image AI just offers one of them. And I found that it was the most easiest user interface to use, so I selected it for this demo. But for your project and maybe other cases, you might want to explore the other YOLO implementations that exist. So to begin, here's some basics. We'll be using OpenCV to work with images. So you can read about the different operations here, but here's a quick summary. So we're going to read in some basic libraries that are great for any data analysis here. And then with OpenCV, we can read in images. So we have an image of a pug and a person, and we're going to read that in right here. We're going to print the shape of this image, and it has 900 by 1300 pixels here, and that is basically these dimensions along here. 3 denotes the color channel, so because this is a color image, and we have red, green, blue, so that's why we have 3 over here. We can show the images inline using matplotlib, so that's what we're doing here. One thing to note is that OpenCV reads in images as blue, green, red, but we want to visualize it, or PLT will visualize it as RGB, so we need to convert it. So this line here just simply converts the colors, so it flips basically the red and the blue here. So as you can see, we flip the colors, then we can show the image, and it shows up like this. So this is how we display an image inline. Sometimes if you're working with a lot of images, you might want to view it larger, and we can view it in a new window. So right here, this code and using OpenCV, we can open it in a new window. So we are going to convert to grayscale, so I can show you what the grayscale looks like. And we can essentially use this show, and that's going to basically open this image into a new window. And this wait key is basically saying that it will stay open until I press any key on my keyboard, and then it'll close it or destroy all windows. So you show that? Yeah, so the pug image opens up here. I can take a look at it. I can press any key on my keyboard, and it will close. So I'm going to press Q and close it. That's how we display images larger, or we can of course change the size, but it pretty much opens in a new window. We can also manipulate the images, so I can look at different color channels. The image, as I said, had 3 color channels. I can take each of the color channels and set it to 0, so it will appear, for example, as red. So for this, I'm making a copy of the image. I am setting the second color channel, which is blue is RGB, so that's G and the blue, so the green and the blue, I'm setting those both to 0. That's why it appears red, and I do that for all the other colors, all the other colors. So I see the red channel, the green channel, and the blue channel here. Those are the basics of OpenCV. We can also do some other interesting things with OpenCV, such as change the look at edges. So right now I'm using very quickly showing you how to use image edge detection. This is called the Canny edge detection algorithm. It was actually built by UC Berkeley computer science professor, but we can very quickly do it in one line of code here. We can see that it shows the edges of any image we pass in. So that's one of the cool features of OpenCV. And a basic computer vision task we can do in one line of code. We can also save images. So if we manipulate it, like we've manipulated this image, we can save it here with this cv2.imWrite method here. Next, I'll be talking about how to work with images. So we're again using the Image AI library, and we're going to be using the pre-trained YOLO model called YOLO.h5 here. So there's basically a variety of things a variety of inputs we can work with. But one thing I want to note here is something called the minimum percentage probability. So as you saw earlier in the other video, each object that it predicts, it draws a bounding box around. And the bounding box has this percentage confidence score or probability percentage, and we can set the minimum. So if we set to 90, only objects with a probability score greater than 90 will appear. And what this will do is it will output this code here will output in an object called detections. It will output each of the objects that we find in the image. So quickly walk through here. We are basically initializing the object, much like we did in like sklearn. We are saying that we're going to use a YOLO model. We we give it the YOLO model, and we give it the weights. This is a file that prerequisites shows how to download and bring into your current repository. And then you basically load them all, and then you run this line here. And this is the line that's actually going to go through and look for objects in your image. So this input image says where the image that you want to input is, and the name of it. This is the name of where we want to put the output image. I'm going to call it city new, and this is the probability percentage that I talked about earlier up here. So I'll walk through what this detection, what this actually is. But for example, when I run this, it'll take a few minutes because it's there's quite a bit of things in this image, and the image is relatively large. But it's going to go through this image and detect all these objects. So it detected a handbag, and this is the probability score, the percentage probability, and then this is the box point or the coordinates for that particular object. So once I run this, it will in real time print these out as it finds them, and then once it's printing these out here, we can basically take a look at this a little bit later and see what exactly is going on here. Look at the different objects and do any type of data visualizations on this. So next, as I said, I'll talk about the detections. So detections is actually it's a list of dictionary objects. Each dictionary is one object that it has found in the image. So detections here, I'm looking at the first three. So the first three dictionaries. The first dictionary, the item is a handbag, and it gives us the name, the label, which is the handbag. The percent probability, so it's a 56% sure that it was a handbag, and then it tells us the coordinates of this point here. So the coordinates of the box, of the bounding box. So it gives us 4 coordinates here, and in 4 elements in a list. The first 2 elements specify the upper left corner, and then the last 2 elements here, they specify the lower right corner. So we took a look at the first 3 elements, but of course there was there's all these elements, these objects were found in this image. So we can also look at this image, so we can read in the image. This is image new, as I specified up here. I can read in this image. Again, OpenCV will bring it in as GRB. I want it RGB, so I need to convert it, and I can quickly show and show the image. So it might be hard to see, but we actually have drawn the image that output actually has these things drawn here, right? It has a little box around each of the items. It has a probability score, and it has the label. It's really hard to see because this image is many pixels, as you can see here on the axis, but it has gone through and it has drawn these bounding boxes around each of the objects of interest, which is, I think, really cool. So with that, we basically collected some data on the image. Let's go through and actually use this data. So using these bounding box points, I'm actually going to go through and crop out these objects of interest. So I'm defining a function here called crop, where I'm basically taking these points and I'm slicing it just like I would do with like a text string. I'm basically slicing out these images here. So you could read through this, but the idea is here I define a cropping function, and then I go through, and for the first 5 objects in detections, I'm basically cropping it out. And I'm just putting in a subplot here, so you can see each object. So it got the handbag, it got the stoplights here, and it got this object. I don't think it's actually a car, so it's actually a mistake here, but that does happen. I want to point that out. And then you crop out the car here. So this is cool if you want to parse through it and maybe some security footage and crop out suspicious items. This is potentially one application of the image AI and object detection. We can also use OpenCV to draw on images. So we got the location of the bounding boxes, and we want to now draw a box around that. The image AI library output image does have a box, but it's kind of faint here, so I want to draw a thicker plot. So I am here basically defining a function here that helps me takes this list that's in this form here, and it converts into 2 tuples, and these 2 tuples are outputted here, and then I can pass these 2 tuples into this OpenCV function here that helps me draw a rectangle. So I pretty much draw this, I'm drawing this image here on top of pedestrians, which is this image that I've read in over here. And then I'm basically drawing this rectangle on this red bag here. So that's one way you can pretty much go ahead and use OpenCV to label images. And you can do text here. You can do other things besides a rectangle. You can do text. You can do circles, ellipses, any polygons, any other types of interesting shapes. So that's one of the great things about OpenCV. It allows you to basically draw on top of any images that you can read in. So that's all the images I'll have. Next I'll talk about videos. So one thing is, the videos, the images are great, but a lot of times if you're going to build some application with object detection, it'd be really cool to work with videos because you have way more information you can collect. You can build some pretty cool applications with videos. So again, Image AI, which I'm using here, has a variety of methods you can use to basically do some operations and object detection on videos. The functions look very similar here. I instantiate the object here. I tell them using YOLO. I read in the YOLO model, the same YOLO model as before. And then I'm using this function here to actually go through the video that I'm going to be predicting objects in. So this video is a dog playing, and I'm using a trimmed version, so it's that, and it's located in the data folder. I'm saying that the output, I'm going to call it, it's going to output like how the other image, the other method outputted an image with the bounding boxes labeled. This function here is also going to output a video but in each frame, it's going to draw a bounding box around the objects of interest. And I can also specify the frames per second, which is the speed of this output video that I'm going to make. And I can put this progress log, so it's going to spit a line or print a line each as it goes through and processes the video. And this video is a trimmed version, but still it's still relatively long. So you have 143 frames. So when you run this code block, it will take 2 to 3 minutes, maybe 4 to 5 minutes to even run. But you just have some patience, and it will eventually complete. And when it's done, you can visualize the output. So I let this run ahead of time because I don't want to have you guys wait for it to run. But yeah, so it will spit this out, and then it will give you the location of the output file, and it saves it as a .avi file. So this is a GIF version I just embedded, but shows you what the output video would look like. We can actually display the video with this code here. So this is basically allowing me to basically read in the video file that we just created, and it loops through it, and then it basically allows me to visualize it. So one little note here is that, again, I am going to convert it to RGB so it appears correctly. And then I'm going to basically, it's going to loop through every single frame, and then it's going to, show is going to basically show the frame, and then it'll loop to the next frame, and it'll show the frame, the next one, and so on. And then this wait key, actually, it doesn't affect the video it doesn't affect the video here, but it's showing it how it's displayed. So if I increase the wait key, it'll speed up the video when it shows it. And if I decrease it, it will make it, or if I increase it, it'll make the video go slower. If I decrease it, the video will go much faster. And I can press Q anytime to quit. So I'll quickly run that, and then I'll put the screen. But here is the image of the window that I created with the video, and I can quickly preview it here. And then when it ended, it just closed. So that's how we can basically make a video and view it in Jupyter Notebook by running this code here. Something you might have realized, it's very nuanced, is that the image that this video file actually produces is a little bit wrong in the color scheme. It's creating this video with an BGR, so it's not the right RGB color. So if you were to open this video up in the directory that I created, you would see that it's the wrong colors. And we can quickly fix that using some code here. So what I've quickly just written a script here that basically reads in the video here, and then I'm making an output object, and then I'm looping through every frame of the input video, and then I'm converting it to RGB, and then I'm saving it. So you can quickly view this again, but it's going to give you the same type of thing where it's showing you in real time, what the thing would look like. So it's another view at it, but it's essentially just fixing the color and saving a new video. So that's what's going on here, and you can read through that. Yeah, so one of the important things or interesting things you might want to do with this type of video object detection is to actually go through and apply a function to each frame of the video. So we want to collect data on what's going on each frame, and we can do that with this applying a function to each frame. So what we've done here is we've defined this function called forFrame, and it's going to apply this function to every single frame of the video. And I basically just use the same code as above, but just add this line here, and it's saying now I'm giving, I'm giving as it's going through and pushing the video through the function, it's going to tell to use this function that I defined and apply it to every single frame. So what is going on here is this for-frame function takes in these three parameters. Okay, so these three parameters it takes in, and what I'm going to do is I'm going to print these out so you can see what they look like. But these are the three parameters that we collect in the images, and they're basically really useful information that we can collect on each frame. And particularly the count array, I'm going to actually save. So I'm going to keep a running list. I'm just going to keep appending that. So I've defined this called count frames. I'm just going to it's the second object here, second input here. I'm just going to keep on appending it to this object. So when the video is done processing, I'll have a list with all these this second input basically appended over and over again, one for each frame. Yeah. So yeah, I will now show you what basically it printed out for each of these for this statement right here. And I only did the first 5 frames because otherwise it would take a long time. But here it is. So for the first 5 frames, I have the frame number is printed out first, which is the first input here. The second input is called output arrays, and then that is printing out this part here, which is it's basically a list, and then each list has all the objects, much like we saw earlier, with has the name, the label, the name, and then has a label, the probability, percentage probability, that probability here, and then the box points, and then that. So for each frame, it has gone through and has given me the frame number, and then a list that contains all the objects that it found, as well as the last one, which is the counts, which says, bear 1, elephant 1, dog 1, person 1. So it's telling me in this frame, how many objects did I find? And that's the thing that we've been storing in this frame counts. We'll get to that later. So we've basically been storing this for every single frame. So as you can see here, first of all, there is some mistakes, right? There is no, you saw the image here is a person playing with the dogs. There is no bear, elephant, but it's picking up, and there's going to be these cases where your model is going to find things that don't exist because however the object appeared in that frame, it might have looked more like a bear, an elephant, and it might have thought it was something else. But that does happen. So I put out the first 5 frames here to take a look at what the output is, but it's great because now we have access to all the information on each frame, and we can actually take this data here and put it into a data frame and make some visualizations on that. And in the next section, I'm going to talk about how we can basically use these error terms here. We can take this data and then help visualize some of the errors that we might be getting in our predictions. So yeah, so I printed out for the first 5, and I just had it run through the last up to 145. All right, so yeah, so this is just to take a look at the other object we created, the count frames. Remember, I was appending that the counts to it. So for every single frame, it just appended what it counted in that frame. So I have all these 1 for each frame. So I'm looking at the first 5 frames here. All right, so now I'm going to look at counting the errors. So we have this list, and this list is 145 elements, 1 for each frame. And I'm going to look at all the unique elements that it found. So across every single frame, it found this unique list of objects. So obviously it should only have a person and a dog, but it had anything from an umbrella, surfboard, handbag, frisbee. So a bunch of really odd objects were found, and that is sometimes going to happen because it might look in a certain frame, it might look kind of odd, and it might predict these things that don't actually exist. So here, what I'm going to do is, it's at this point it's just a dictionary and list, so you can do some simple indexing into that and some manipulation to get into a data frame. So I've basically pushed it into a data frame here, and it shows us that the dog appeared in 137 frames out of the 145 frames. The person was in 135 frames, and so on. So it's good that the dog and the person were appearing in most of the frames, right? And you have these other things that don't actually exist appearing in only a few frames. And then I can take this data frame now and I can plot it so I can see, as the dog and person in most of the frames, and then these other objects were in a few of the frames. And that gives us a good perspective on, how good our model is actually performing. And we can see that, it's pretty good, right? It's predicting the dog and person, so we're doing well there. And just some side notes. So we don't really want these. These are mistakes the model made. So how to address this? Well, we can maybe increase the minimum percentage probability. Now these objects, it probably have a low percentage probability. So we can increase that, maybe remove these objects. One thing we can do is also look at average it over maybe a second. So we could look at some grouping of time. So maybe every 5 frames, we will, take this data here, but we will look at every 5 frames, and we will take the average of the output count over every 5 frames. So in that case, in this case, the elephant appeared quite frequently, but usually something like the elephant would only appear like, maybe one frame every like in the 60 frames in a second. So if we look at, the second and we do some aggregation over the seconds or minutes, then we can potentially remove some of these outliers that appear very infrequently, maybe one frame every once in a while. And there's some methods that are built in. There's a per second function, a per minute function that we can use readily off the ImageAI documentation. So I encourage you to take a look at that if you are having all these outliers appear. As an additional side note, there are something called custom trained models. So you might have realized that I was only using pre-trained models, the YOLO.h5 for all the examples here, but you can also custom train your models using the ImageAI documentation as well. That's it for the object detection using ImageAI and OpenCV demos here. But again, I encourage you to take a look at other YOLO implementations if you're interested in building a more complete and maybe more complex model.